Wanted to work through a problem that involves induction. It involves Faraday's law of induction. It involves concepts of magnetic fields, magnetic fluxes, and putting all those ingredients together. So in this particular example, we're asked to imagine a rectangular loop of wire, 1 centimeter by 1 centimeter, area 1 square meter. That loop of wire is placed inside a solenoid. The solenoid, a chain of many loops of current carrying wire. That solenoid has a length of 20 centimeters. It has 100 turns and it's carrying a current of 3 amps. So that solenoid is producing a magnetic field uniform throughout the walls, the body of the solenoid. And it's producing a magnetic flux through the coil that is placed inside the solenoid. The solenoid, we're then told, is switched off. Its current is turned off over a time interval of 3 seconds so that there's a changing field in that period of 3 seconds. There's a changing flux through the coil in that period of 3 seconds. And that's going to induce a EMF in the coil over that period of changing flux, changing field. We've got to figure out that EMF. I'm going to figure it out in 2 steps. Firstly, I'm going to think about when the solenoid is on. When the solenoid is on, there's a magnetic field. I'm going to calculate that. When the solenoid is on, there's a magnetic flux through the coil. I'm going to think about, calculate that. Once I've got the field and the flux when the solenoid is on, I'm then going to imagine that moment when we turn the solenoid off, when we lower the current in the solenoid. Then we've got changing fields, changing fluxes. Then we've got induced EMF. I'll calculate the induced EMF at that point. I'm going to start the problem by making a sketch and by noting the things that I know and noting the things that I want to calculate. So let me go ahead and make the sketch. Okay, so here's my sketch. In the center, this rectangle is the square coil. And outside here, this circle is cross-section through the solenoid. And so this is the geometry with the square coil inside the circular cross-section solenoid. I've noted the things about the solenoid that I were told in the question. So the length of the solenoid is 0.2 meters. The solenoid has 100 turns. That means it has, this is lowercase n, the number of turns per meter. It has 500 turns per meter. That's 100 divided by 0.2 meters. And it has a current, finally, that's 3 amps. So these are all the quantities about the solenoid that we know. We also were told, I noted these over here on the left-hand side of the sketch, the area of the coil is 1 centimeter squared, which is 10 to the minus 4 meters squared. And the magnetic field, the flux, the current change over a period of 3 seconds. So as I say, my first step is going to be to think about the field and flux while the solenoid is on. Calculate the field of the solenoid while it's on, and calculate the flux through the coil while the solenoid is on. And then, not only that, I'll turn to the EMF. So the field through the solenoid, the field created by the solenoid, that's B. That field is mu naught lowercase n I, magnetic permeability, times the number of turns per unit length, lowercase n, times the current flowing in the solenoid. I know all these numbers. So the magnetic susceptibility is 4 pi times 10 to the minus 7 Teslas meters over amps. The number of turns per unit length, that's 1,000 turns per meter. And finally, the current, that's 3 amps. if I multiply those three quantities together, that's going to give me the magnetic field. I got a value as 1.9 millitesla, 1.92 10 to the minus 3 teslas. So that's the field when the solenoid is on. When the solenoid is on, there's a flux through the coil, through the square loop. That flux is due to the field of the solenoid. The field is perpendicular to the page. The field is coming either out or into the page, depending on the sense of the current around the walls of the solenoid. That field is perpendicular to the face of the square loop, i.e. that field vector B is parallel to the vector A, representing the surface of the square loop. And so in this particular case, the flux is going to be B times A times the cosine of 0 degrees. And so that's simply the magnetic field of 1.9 times 10 to the minus 3 Tesla times the cross-sectional area of the coil is 10 to the minus 4 square meters. And if you calculate that product, I got 1.9 times 10 to the minus 7 Webers. Webers is the units of flux. It corresponds to Teslas times meters squared. 1 Weber equals 1 Tesla meter squared. I didn't need my calculator for this calculation. It was 1.9 times 10 to the minus 3 times a factor of 10 to the minus 4. So it's 1.9 times 10 to the minus 7. So this is all about the solenoid when the and the flux when the solenoid is on. Now we can go ahead and calculate the EMF that's created when the solenoid is turned off. I'm just going to worry about the size of the EMF. So I'm not going to worry about the sense of the EMF, the direction of the current, because I never knew the direction of the current in the solenoid itself. The size of the EMF is the size of the change in flux divided by the elapsed time. And I know both of these. The change in flux, well, the flux was 1.9 times 10 to the minus 7 Webers, and the flux became, with zero current in the solenoid, 0 Webers. So the change in flux is the original flux. That's 1.9 times 10 to the minus 7 Webers. And the time interval, well, we were told the time interval in the problem, it took us 3 seconds to lower the current from the original current of 3 amps to 0 amps. And so that time interval is 3 seconds, 3.0 seconds. And so all I've got to do is divide the 1.9 times 10 to the minus 7 by a factor of 3. And that number I've written down is 63 nanovolts. So a nanovolt is 10 to the minus 9 volts. So this is 6.3 times 10 to the minus 8 volts. So it's a tiny, tiny voltage that the effect of induction, electromagnetic induction, has produced. But there is a small EMF, there will be an induced current in this square loop as we turn off the field by turning off the current in the solenoid. Anyway, that's an example of induction and Faraday's law of induction and concepts of magnetic fields, magnetic fluxes. Induction was, the discovery of induction was a huge moment in scientific history because it was the beginning of the second great unification in scientific history. It's the unification of electricity and magnetism. It's the joining together of electricity and magnetism that were thought to be separate forces, but were realized in the end to be different faces, different components, facets of a single electromagnetic force.